Our first speaker of the day is James Halliday. Yeah, there you go. And you're all set up? We're all good, Carl? I believe we're going to start a few minutes early here. As long as you want. So I'm going to hand it over to you.
Hang on. There we go. It warms up, I guess. It's a cold mic. Hello, everyone. I'm here to talk about a silly fun project that has real, possibly useful components of it. It's a peer-to-peer calendar. I apologize for starting early. This was not my decision. This decision was forced upon me, but we'll make do. It's early for me as well. So, let's get started with the problem. I don't know how many times any of you have been traveling. I travel quite a lot. I'm often on pretty terrible internet. I was in really bad internet in April in Guyana, where there's a satellite connection. The maximum ping time I saw was about 31 seconds. So something went terribly wrong there. And of course, websites like Google Calendar, here I did just a file save as in the browser just to see how much payload I was getting. So for the month of June, so I've saved on Google Calendar about maybe 100 bytes of information, and to load that 100 bytes, I've had to download here about 3.5 megabytes of data. This is a bit strange. Why do we use these internet services where we're pulling down so much information for things that pretty much only we care about? We could just as well run the software on our own computer. So why don't we do that? That would be nice. Another problem is that now Google, an evil advertising company, has all of our precious data, which is, I'm sure, is good for their shareholders, but it's not so great for you and I, being people who don't like to be surveilled very much. So I've been working a lot with these kinds of systems that instead of uploading all of your information to a cloud provider, nobody owns them. They just exist. So there are a few great examples of these kinds of networks. BitTorrent is a good example. It just sort of, nobody runs it. There is a company that is also evil that tries to make money, but they can't really, there's only so much they can do with that network because it was designed in such a way that even they can't steer it in a too terrible of a direction. But I think the most important part is that we can use our own computers. And that means our own computers, not just computers that we run as servers, but our phones, my laptop right here, our desktops sitting at home, that kind of stuff. So why don't we make the web great again? And how to do that, I think, very effectively is to use peer-to-peer techniques. So one important thing when you're building a peer-to-peer system is that everything is a client. There is no other type of component to a fully distributed network. Sometimes you have hybrid networks, and often you have to make a few sacrifices here and there, but for the most part, everything has to be done at the edges. So this is, I think, kind of foreign to us web developers, where maybe we got our start making silly things where, you obviously don't want to do authentication in the client, right? In a web page, you don't want to put the password in the JavaScript code that you also deliver to the client. So you have to kind of resign that part of your brain for a moment and think a little bit differently about how to do this stuff. I picked up this great word in Germany by these people who think this is an English word. Despite having English components, it is in fact a German word. Counter-anti-disintermediationism. But the basic idea here is that we can build systems where instead of mediating our transactions with third parties that provide hosted services, we can provide these things cooperatively for each other. So a few things also to kind of perhaps prime your brain to accept some of these ideas that I've learned is that it can be really helpful to avoid certain patterns that you might expect with a centralized system, such as global consensus. That includes things like having naming systems, having conflicts, but the important thing for conflicts is just to not have that problem in the first place, and just to be more pluralistic in how you approach data structures. And I'll get a little more into that with some specifics. This is also a really good technique. Sometimes I've found in life generally and in computer systems, the best way to solve a problem is just to not have that problem in the first place. Just engineer your life in such a way that you are not even solving certain categories of problems. Like, I don't like to build user password systems, so I've just taken certain life decisions that steer me away from that whole category of things that I don't like to build. For example, for me. So let's get into some architectures. This is a really powerful technique for building these kinds of peer-to-peer systems. It's called a kappa architecture. And I like to call this category of ownerless systems an architecture, because it's an architecture, but it's also an architecture. The basic idea here is that you have an append-only log that serves as the source of truth. So you always write true things to the log, and they're true by virtue of being in the log. They're not necessarily true facts themselves, but you append observations to a log that grows over time, and then you build indexes called materialized views that can answer questions more quickly from that log. So instead of having to read every document to answer a query, you can consult one of these materialized views, and they'll answer these kinds of questions more quickly. So one big project that I've built recently with these techniques is an offline peer-to-peer map database called OSM P2P, and it's being used in Ecuador right now, hopefully more places soon, to map things in remote communities that are completely offline or have very poor internet access or very sporadic internet access. So this is a really useful data model in places that are not California, that are not Western Europe, in places that are the real world, where you can't really take things like cell coverage for granted. And I think even in like America, for example, that's an assumption that kind of breaks down. If you're in a tunnel, if you're traveling across the country, if you're on a train, if you don't have enough money to afford a data plan, they're quite expensive actually. If you're a kid and you don't have a credit card, all kinds of things where these data models can really be very useful for building systems that real people can use to solve real problems. So let's get started with this calendar. I think this calendar covers a lot of ground, which is why I chose it as a little topic. It's also something that's been fun that I've been working on lately. So we're going to cover hyperlogs, some different kinds of materialized views that we can build on top of the hyperlog, some wacky regexy date parsing stuff that I've had to write to make this all kind of work, and also some like text formatting things that are kind of fun. So to start with, hyperlogs are an append-only data structure where each document that you add points to 0 or more predecessor documents. So this is just like Git, where as you make a commit, the commit hash points back at the hash of the previous document. And when you do an operation like a merge, you point back at multiple documents. So in Git, you have this idea of a head, a rolling head that is the hash of whatever the most current document is. And for each branch, you might have a separate hash. So here we're using the same kind of idea, which is called a Merkle DAG, for building a data model that works really well for multiple writers who are writing offline over the course of perhaps weeks. So we don't have any sense of consensus. We don't have any sense of global consensus. We don't really need any kind of a model that enforces constraints like that, because that is a model that I found works quite well in environments where you're not online constantly and you're not. Yeah. So here's some code about how you would append a document to hyperlogs. So the main thing that you do is you create a database with LevelDB, which works also in the browser. So all of the code that I'm going to be showing you also runs in the browser. If you want, you can just browserify it up, and instead of requiring level, require level-browserify, and it should all work. So then all that you need to do is call log.add, and you pass in the array of ancestor keys, which are the predecessor hashes, and then you can pass in a value and get back a new key and a new document. And then to list out all of the documents, you call create read stream, and you can also give that some options like live or tail. If you want to list things since a certain hash, you can do something like the CouchDB changes feed with LevelDB or with Hyperlog. It's all quite straightforward. There isn't a lot in the API, which I like in the abstractions that I use, so I use it a lot. So the next piece in this whole wacky system is Hyperlog index. This is a module that I've been using a lot to build these kind of materialized views on top of a Hyperlog. How it works is you give it a different level DB, and there's a module called sublevel or sublevel down that makes it easy to kind of prefix out a database. But what I've found is that for building materialized views, it's quite convenient to use a separate level DB data directory, because then if you change your mind about how your data schema works, you can just delete that directory, and this module will regenerate your indexes. So if you've ever had to do migrations in a relational database, this, I hope, will seem very convenient in comparison. I really like this approach a lot. So then in Hyperlog index, what you do is you get every document in the log, one by one, and you store that document however you want. So if you, for example, for that map database, I've got a spatial index that I built. You could use a separate level DB. You could use a relational database if you want. Like you could use SQLite. It doesn't so much matter. And then you call next, which is a function. That just tells the index to advance. There's also a ready method, and that just kind of gives you a hook into when the indexes are all caught up with the latest known version in the log. So you can, if you need to, you can wait for your database to kind of catch up at the index layer, which is nice for the programming model. Some other things we can build. I've got this package, HyperKV. I've used this in a lot of different projects at this point. It's a key value store built on Hyperlog using Hyperlog index. And the important thing that I've learned about building these kinds of systems, there's this great idea called a multi-value register conflict strategy, which is some fancy words, not unlike that German, but it has spaces in it. That means when you get a key out of the database, instead of getting a single value, you might get multiple values. And if you make that trade-off, and if you kind of push that to the user interface, then you don't have a lot of problems that you would otherwise have, enforcing consistency, handling conflicts, that kind of stuff. Instead, you have a good data model that lets you do merges effectively from the interface and presents the plurality of data that you might have, because the only thing that you can say when you have multiple values is that you have multiple values. There's no piece of information that is more correct than another one in that case. It's a human problem, and you have to present a human solution. So here's what that looks like. You pass it a level DB as well, and you pass it the Hyperlog right here. Then you call just ordinary methods you might expect from a key value store, like put and get. So this program will just print out what you put into it. It's important when you set up the Hyperlog to pass the value encoding of JSON, because HyperKV expects that. Yeah, so this idea of having multiple values, which you can see right here. In this case, values is an object where the keys are the hashes and the values are the documents that you get back. And when you have this idea, you just don't have to solve a lot of problems. So I like not solving problems if I can get away with it, and that's one technique for doing that. So where exactly am I going with all of this, all of these various lengths of wire when you want to learn about a spaceship? So what we're going to do for this calendar is we're going to write events into our Hyperlog, things like the event name and title and time information. We're going to do that by writing into a HyperKV so that we can update the events, because HyperKV has a mechanism for that with this multi-value conflicts strategy. We can use, and HyperKV of course uses Hyperlog index to do that. We're also going to need some modules for messing around with time parsing. So this was a fun while. I wrote some of these a long time ago, and one of them more recently. So have you ever had a problem where you have a wacky string like next Friday at 12:30 p.m.? Parse messy time, it gives you a string. That might even be the correct answer. So I wrote this module. It can sort of parse some things sometimes. It's good enough for a prototype anyways. It understands things like tomorrow at noon. That might work. Yeah. Oh, midnight. Well, at 12 p.m. There's probably a bug for noon, but anyways, you get the idea. The second piece that we'll be using uses parse messy time. It's called parse messy schedule. And you set that up with a recurring event. So if you want to do something like, say, for example, every Thursday can be at 7 p.m. is JavaScript study group. So we can make an event with parse messy schedule, and then we can call these two properties, next and previous. And if we call next with a date, then you get a new date, which is relative to the date that you've passed in, what is the next occurrent of this event? So you can call date repeatedly, like this. Well, if we set up date first, we can repeatedly call a date, and we can get a stream of events in the future. And we could also get events in the past. So this is really good if we want to create a bounded set, for example, for a monthly display on our calendar. So if we want to get all of the events in June, we can use the current day. We can seek back until we get an event that's outside of our bounds, like something that comes before June 1st and something that comes after June 30th or whatever it is. Okay, so we've got some methods now to deal with dates and scheduling. I've encapsulated those pieces into a module called CalendarDB, and this just provides a more mutable interface with persistence. So you can have a lot of records, and you can do queries like given greater than and less than in terms of dates, you can dump out everything that is between those two values. With that, I wrote this module called Hyperlog Calendar Index, which uses Hyperlog Index to build a materialized view on top of a hyper-KV that writes to the hyperlog. So all of these layers, and finally, now we're getting to the point where we can have an actual calendar that we can look at. But first, we'll need to implement a text-based user interface for the command line. So I have this other module, calendar month string. That's pretty fun. So you require calendar month string. You can give it a date if you want, or you don't have to. And it provides you back something that looks like the cal commands. If any of you have used this, I use it constantly. It's fantastic. I don't have -3 support yet, and I don't have year support, but I have the simple part of it done where you can have a date like that. It's pretty fun. You can also pass in ANSI codes that will apply to certain points. Might even be able to do that. So, for example, if I want the 15th to be a color, I think I pass in something like that. Yeah, there we go. So that one can be red. It's actually a fuzzy ANSI string, so you can set the background color to red. We could set the foreground to like cyan, whatever you want. It's pretty fun. The last piece now is this module text layers that takes multiple text blocks, like a calendar, for example, maybe a list, and it just sort of offsets them and combines them into a single text string. Like, I could do that with ANSI codes and offsets, but I like this approach a little bit better because then you can not have to do as much parsing. So putting all of these pieces together, we have a command. It's called norcal, and the colors are a little bit hard to read, but this is the dates. We have scheduled events like JavaScript study group, hardware hack night, flight to PDX happened back on the Sunday, and we can add things. So to just test things out, I'll use a different database. This is just a file that I'm going to use for testing. You can add events, and you can give them titles. So if we say every Monday will be will be, this is the title parameter, circuit etching night every Monday at 8 p.m. maybe. So now, with our new calendar, we see that we have circuit etching night. It happens every Monday, which is a little bit hard to read on the screen, but all of these events here on Monday are taken account for. The last piece, though, is that what if we want to share our calendar with someone else? So right now, I don't have that feature implemented, but let's go ahead and write that into NorCal right now, because it's actually quite simple. And I didn't do that before my talk, because I'm not prepared. So what we can do is, here is the code. We have our commands add. You can also get a list of events with the query commands, which just dumps out a list. I think by default it's the current month. That just gives us all of the records. So what we want to do is add a command to synchronize our calendar. So we can add a new command called sync. Previously, when we set up the calendar has the hyperlog attached as a property. So with hyperlogs, the really great thing about having append-only logs is that replication is very simple. You just need to concatenate them, more or less. There's some more sophisticated ways to improve the performance, but simple concatenation will get you a long ways. So there's a replicate method, so we can call cal.log.replicate. This is a duplex stream, so now we need to hook up some endpoints. We need the input side and the output side. So what I like to do in this case is to use standard in and standard out. So I'm going to pipe standard in into my calendar replication, and I'm going to pipe the output side to standard out. So if I run my calendar now, I can do NorCal sync, and I'll use the database that I made from just a moment ago, the one with circuit etching night on Mondays. So I can run this command, but the problem is I need to run another instance of NorCal that hooks up both ends, the standard in and the standard out. So I've got a little tool called dupesh on npm that runs two programs. The first program, it takes the standard out of the first, pipes it into the standard in of the second, and it pipes the standard out of the second back into the standard in of the first. So it sort of just hooks up two programs. It's a very nice way if you're dealing with distributed peer-to-peer replication protocols to play around, because standard in and standard out are very easy to write. Then you don't have to bake in particular protocols into your program, like WebSockets or WebRTC or something like that. So I can replicate that into my main calendar, which has a default database set. So if I do this with our new sync feature, dupesh doesn't always end correctly, some bug that I haven't figured out yet, but it should all be replicated. So now if I type NorCal, we'll know for sure. And indeed, now we have a new event, circuit etching night, on Mondays that showed up on our calendar. So there we go, peer-to-peer replication for our calendar. One problem, though, is that, so that works if we want to share our entire calendar. But that's, I mean, if we're building a new calendar from scratch, we probably want to have better privacy, like more granular privacy controls than something like Google Calendar. So a few calendars that are hosted and desktop software sort of address this in different ways. Like Outlook, I've heard, has a feature where you can share sort of like the mask of which events are scheduled without disclosing the contents. So it just shows which times you're available, but it doesn't show necessarily what the contents of those events are. This is useful for scheduling if you just want to make sure that someone is available in a certain time interval. So I think we can do even better than that, though, because what if we want to share, what if I want to share my location? What if I want to share a kind of like broad view of that location, like what country I'm going to be in, or like even what continent I'm going to be in? Because I might want to share that publicly with the entire internet, and I don't want to like, tell people my exact coordinates at all times. That seems bad. Also, I might want to share just particular other pieces of information. So to do this, we can build a capability system. So capability systems are really useful ways to build granular permissions. So I think one that might be familiar to people is the Unix file system. You have a read permission, you have write permission, and you have execute permission. Also, for directories, when the executable bit is set, you can list out the contents of a directory, which is a quite useful thing to have built into a capability system. So we can do the same thing with cryptography. And what's nice about using cryptography to do this is it means that we can share the data for our calendar with everyone, and everyone can help us host that. So our friends, like whenever we share calendars, we can help host each other's calendar without disclosing the contents of our calendar. And one way to do this, and there's a few ways that I've kind of been poking at, is to use HMACs as a derived key system. So with a few modules, we can build one of these. So just with the crypto module in Node, or if you want to do this in the browser, you can use crypto-hmac, which is a little bit smaller in bundle size. We can, from a root key, which is in this case a 32-byte payload of just secure random data, you can generate derived keys for different property names. So if you imagine that we have an object with these properties, prop name 1, 2, and 3, with values, then we can create custom keys for each property, and then we can encrypt those properties separately so that we can share particular keys without divulging the whole thing. But also, if we want to share the entire document, all that we need to do is share the root key that generated all of those properties. So that's a little bit more efficient if you want to do replication. So here's what that looks like with this module called Chloride, which implements the NaCl algorithms, which are really fantastic because it's more difficult to shoot yourself in the foot with these algorithms than with many other crypto packages, where it's notoriously difficult to get them correct. So NaCl is pretty good. There's this module for doing symmetric encryption called Crypto Secret Box. You pass in plain text, a nonce value, which is a random piece of data that you need to store along with your encrypted payload, and the individual property keys that we've delegated with the root key. How that might look if you want to store these files, so here, for example, we can write them out to a file, or we could publish these to our hyperlog, for example. We need to store the nonce and the ciphertext that we can generate with Crypto Secret Box. So once you do that, also another way, this approach discloses the property names, but if you want to get away from that, you can add another property and use an array instead. So this additional property would just store the array of the keys. And once you do that kind of a trick, then you can store the list in this array structure. And then the list would have the offsets to the other keys. This is the same idea as the executable bit in a Unix file system that lets you list directories. So it's a kind of the same ideas pop up in a lot of places. So in our capability system, we'll have individual property keys. These are kind of like read access to those fields. We can have write access if we give the root key for an object. Like, for example, if we have a shared event, it's going to have a root key, and we can give away the root key to our friend, and also to our log, publish the public key of our friend to our log. And that way they can, that way everyone who synchronizes our calendar knows to also accept updates from that person. And then the keys property is like the list. So one problem is if we have separate keys for everything, then if we want to synchronize a lot of data, I mean, calendars are not really a lot of data, but you can imagine a different use case where the data payloads might be larger. There are other tricks we can employ with this capability system. So if we have a root key that's derived from another root key, we can build this nested structure where maybe we have different pieces that are kind of build this hierarchy. So we might have years and months and weeks and days that each have a derived property. And you can kind of build a more complicated structure for that. So what that might look like is if we have this event, here we have a location and title. All of these properties are going to be encrypted. Then we generate a nonce and our prop keys for each value with the plain text. And then with this encrypted object, that's the one that we can actually store on our hyperlogs. That has just the nonce and the ciphertext. So with this kind of technique, we can, if for example, I want to share an entire month with someone, the complete contents, then I can just give them the month key, and they can derive all of the properties from that. They have to unpack things, but their calendar program will be unpacking that. The nice thing is that if I want to share that data with someone, the data will already be on their system. Like, they'll replicate my entire log and then just decrypt the parts that they need as necessary. And if I want to revoke that access, I can just re-encrypt that section so that the key changes. Like, you can't go back in time and unshare something, but you can make sure that new updates, they won't see access to the new updates. So here's what it might look like to uncrypt single property. The Sodium API has all of these weird names for things, so you use crypto secret box to encrypt, and crypto secret box open to decrypt. They didn't think to just put encrypt and decrypt, whatever. Some weird terminology issues here, but it's the basic idea. If you want to decrypt a whole event, this is what that would look like, where you have to unpack the list, and then you have to unpack the individual properties. If you have the root key, and for example, a whole day, then you have to unpack the list of days, and then you have to unpack for each day the list of properties, and then unpack each property separately. So that was a lot of code. Working on a module for this so that you won't have to write any code that looks like that at all. You'll have a nice thing that's nice, but haven't finished that yet. But let's just imagine for a moment that this existed. Wouldn't that be nice? I think it would. So thanks.